There are crystals forming somewhere right now, deep underground where no one can see them, where temperature and pressure create conditions that allow atoms to arrange themselves into patterns, finding positions that are stable, that repeat, building structures that grow slowly, molecule by molecule, layer by layer, the process taking years or centuries or longer, time operating on a scale that makes human lifetimes seem brief, that puts our sense of urgency into perspective, crystals growing. In the dark, patient and persistent, following rules that are built into the nature of matter, into the way atoms attract and repel each other, creating order out of what could be chaos, finding arrangements that minimize energy, that create stability, patterns that repeat in 3 dimensions, extending outward from a seed, a starting point, growing as long as conditions allow, as long as there's material to incorporate, as long as temperature and pressure remain within the right range. The word crystal comes from a Greek word meaning ice because the ancient Greeks thought quartz was ice that had frozen so hard it couldn't melt anymore, permanent ice, eternal cold made solid, which is wrong but understandable, quartz being clear and hard and cold to the touch, properties that ice shares, at least superficially. The connection between crystals and ice isn't entirely false though, because ice itself is a crystal, water molecules arranged in a hexagonal pattern, each molecule connected to 4 others through hydrogen bonds, creating a structure that's open, that has space in it, which is why ice floats, why it's less dense than liquid water. The molecules held in a rigid framework that takes up more volume than the same molecules moving freely in liquid form, sliding past each other, breaking and reforming bonds constantly, fluid and dynamic rather than fixed and structured. Snowflakes are ice crystals, forming in clouds when water vapor condenses directly into solid form, skipping the liquid phase, the molecules settling into their hexagonal arrangement, building outward in 6 directions because of the way water molecules bond, the angle between hydrogen and oxygen creating a geometry that favors 6-fold symmetry, each snowflake growing as it falls through the cloud, encountering different conditions, different temperatures and humidity levels, each variation affecting how the crystal grows, whether it develops long needles or broad plates or intricate dendritic patterns, branches sprouting subbranches, creating complexity. No 2 snowflakes exactly alike because no 2 follow exactly the same path through the cloud, experience exactly the same sequence of conditions, the differences creating infinite variation within the constraints of hexagonal symmetry. Each snowflake unique but all of them recognizably related, family resemblances that come from shared geometry, shared molecular structure. Crystals on Earth form mostly underground, in cavities and cracks in rock, spaces where mineral-rich water can seep in and deposit material, or where molten rock cools slowly enough that atoms have time to arrange themselves into ordered patterns rather than freezing into the disordered structure of glass, which is what happens when cooling is too rapid, atoms getting locked into whatever positions they happen to be in when the temperature drops, unable to rearrange, unable to find the lowest energy configuration, stuck in a higher energy state, a metastable condition that persists not because it's stable but because there's no path to reach the more stable state, the energy barrier too high to cross, at least at low temperature where molecular motion is limited, where atoms don't have enough thermal energy to break free and rearrange. Quartz is one of the most common crystals, silicon dioxide, each silicon atom bonded to 4 oxygen atoms and each oxygen bonded to 2 silicon atoms, creating a 3-dimensional network that extends throughout the crystal, the same pattern repeating over and over, unit cells stacking together, the whole structure held together by strong covalent bonds, which is why quartz is hard, why it resists scratching, why it can survive for millions of years exposed to weather and erosion, gradually breaking down but slowly, persisting long after softer minerals have dissolved or worn away, quartz sand accumulating on beaches, the remains of crystals that formed deep underground and were brought to the surface through geological processes, uplift and erosion, mountains rising and wearing down, the crystals that formed inside them exposed and eventually freed, carried by water to the sea, ground down by tumbling against other grains, becoming smaller and rounder but still crystalline at the molecular level, still maintaining that ordered atomic structure even as the overall shape becomes irregular. Some crystals are colored, the color coming from impurities, atoms of other elements substituting into the crystal structure, sitting in positions where they don't quite fit, disrupting the perfect order slightly but not enough to prevent crystallization, just enough to change how the crystal interacts with light, which wavelengths it absorbs and which it transmits or reflects, iron impurities making quartz pink or purple, chromium making it green. The colors often beautiful, prized, collected, cut and polished into gemstones, though the distinction between a gemstone and an ordinary crystal is mostly about rarity and appearance, about cultural value rather than any fundamental physical difference. Both are crystalline solids with ordered atomic structures. Both follow the same physical principles, the same rules of chemistry and geometry. Diamonds are crystals of pure carbon, each carbon atom bonded to 4 others in a tetrahedral arrangement, creating a structure that's extremely rigid, extremely strong, the hardest natural material, difficult to scratch or break. Though diamonds will burn if heated in air, the carbon reacting with oxygen to form carbon dioxide, the diamond literally disappearing, turned into gas, which seems wrong for something that's supposed to be eternal, that's marketed as forever. But diamonds are just carbon in a particular arrangement, and that arrangement isn't the most stable form of carbon at surface conditions. Graphite is the soft material in pencils, carbon atoms arranged in flat sheets that slide past each other easily, the opposite of diamond's rigid three-dimensional network. But the transformation from diamond to graphite is so slow at room temperature that it effectively never happens, diamonds persisting for millions or billions of years, metastable but secure, trapped in a high-energy form that can't easily relax into the lower energy structure, the activation barrier too high, requiring temperatures and pressures that don't exist at the surface, though they do exist deep underground where diamonds form, 100 miles down or more, in the mantle where pressure is intense enough to make diamond the stable form, where carbon crystallizes into the compact structure we recognize, growing slowly until volcanic eruptions carry them upward, shooting them to the surface in pipes of molten rock that cool into formations called kimberlite, strange vertical structures that cut through the surrounding rock, diamond mines following these pipes downward, extracting the crystals that formed in conditions that no human will ever experience directly, pressures and temperatures that would instantly crush and vaporize anything biological, hostile beyond imagination but perfect for making diamonds. Salt is a crystal too, sodium chloride, the table salt that's used for seasoning, each sodium atom surrounded by 6 chlorine atoms and each chlorine surrounded by 6 sodium atoms, alternating in a three-dimensional checkerboard pattern, the atoms held together by ionic bonds, sodium giving up an electron to chlorine, becoming positively charged, chlorine accepting the electron and becoming negatively charged, opposite charges attracting, creating the bond, the structure building outward from a seed crystal, growing in solution as water evaporates or as the solution cools and becomes supersaturated, no longer able to hold all the dissolved salt, the excess crystallizing out, forming cubic crystals because of the way the atoms stack, the geometry of the underlying structure expressing itself in the shape of the macroscopic crystal, cubes within cubes, a pattern that repeats from atomic scale to visible scale, the connection between small and large direct and beautiful evidence of how structure at one level determines structure at another, the micro determining the macro. Growing crystals from solution is something people do as experiments, as demonstrations, dissolving salt or sugar or alum in hot water and letting it cool slowly, watching crystals form on a string or on the bottom of the container, the process visible, happening over hours or days, fast enough to observe but slow enough to see details, to notice how crystals start small and grow larger, how they develop faces and edges, how the shape emerges gradually, the same shape appearing over and over. Because it's determined by the internal structure, by the way molecules or ions pack together, angles and distances fixed by the size of the atoms and the type of bonds between them, the macroscopic shape reflecting microscopic reality, what you see expressing what you can't see, the visible revealing the invisible. In caves, crystals can grow to enormous sizes, conditions there being particularly favorable, stable temperature and humidity, mineral-rich water seeping through rock and depositing material slowly, drop by drop, year after year, century after century, building formations called speleothems, stalactites hanging from the ceiling and stalagmites rising from the floor, both of them crystalline, mostly calcite, calcium carbonate, the same material that makes limestone and marble, though in caves it grows as clear or translucent crystals, sometimes tinted by impurities, sometimes pure and colorless. The crystals often large, sometimes enormous, weighing tons, taking thousands of years to form, each layer adding thickness, adding length, the formations growing slowly toward each other, stalactite descending and stalagmite ascending, sometimes meeting in the middle to form a column, a continuous crystal structure connecting floor and ceiling, though continuous might not be quite right, because there are probably boundaries between individual crystals, places where one crystal ends and another begins, the boundary invisible or nearly so, the crystals grown together, fused, sharing the same orientation, the same atomic lattice, aligned well enough that the discontinuity doesn't matter, doesn't create a weak point or a visible seam. There are caves where entire rooms are lined with crystals, the walls and ceiling covered in points and faces that catch light and reflect it, creating a glittering interior, a space that seems almost artificial, designed, too symmetrical and regular to be natural, though it is natural, entirely natural, formed without intention or purpose, just chemistry and physics operating over time, creating beauty as a side effect, as something that happens when matter follows the rules it must follow. When atoms find stable arrangements and build outward from them, creating patterns that humans find aesthetically pleasing, though the crystals didn't form to please anyone, didn't form for any reason, just formed because conditions allowed it, because energy was available and atoms were present and time passed, the combination sufficient. In one cave in Mexico, crystals grew to extraordinary size, selenite crystals, translucent white, some of them longer than telephone poles, wider than a person, weights measured in tons, the largest crystals ever found, growing in a chamber filled with mineral-rich water, heated by magma below, the temperature high enough to keep the minerals in solution, allowing them to crystallize slowly over the course of thousands or millions of years, the chamber eventually being drained by mining operations, exposing the crystals, making them accessible, though accessible might be the wrong word because the chamber is still hot, almost too hot for humans to survive in, requiring cooling suits and limiting visits to minutes, the environment hostile despite being crystal-filled, beautiful but dangerous, a reminder that nature doesn't make things for us, doesn't consider our needs or preferences, just operates according to its own logic, following physical laws that apply everywhere, that don't care whether the results are convenient or hazardous, useful or deadly. Crystals have been valued by humans for as long as there have been humans, probably before that, prized for their clarity or color or rarity, collected and traded and worn as decoration, sometimes attributed with magical properties, healing powers, spiritual significance, beliefs that persist today despite no scientific evidence, crystals sold as therapeutic objects, as tools for wellness, claims made that don't hold up to testing, that seem to work only through placebo effect, through belief, itself creating outcomes, which is interesting in its own way, the power of expectation to influence experience, but not evidence that crystals have any inherent power beyond their physical properties, their hardness or their optical characteristics, the way they interact with light, bending it or splitting it into colors, refracting and reflecting according to rules that are well understood, that can be calculated and predicted, Nothing mysterious, nothing beyond physics. Light moves through crystals at different speeds depending on direction, in many crystals anyway, ones that aren't cubic, where the atomic structure has different properties along different axes, causing light polarized in one direction to move at a different speed than light polarized in another direction, the difference creating interesting optical effects, birefringence, where a single ray of light entering the crystal splits into two rays following different paths, exiting at different angles, creating a double image, everything seen through the crystal appearing twice offset, a strange effect that's easy to demonstrate with certain crystals like calcite, Iceland spar, where the birefringence is strong enough to be obvious, looking through the crystal at text and seeing two versions of each letter, both clear but separated, the light having been divided by the internal structure of the crystal, by the asymmetry in how that structure interacts with electromagnetic waves, with light, which is just oscillating electric and magnetic fields, waves that propagate through space or through matter, affected by whatever they pass through, slowed by dense materials, bent at boundaries between materials with different densities, split by materials with different properties in different directions. Some crystals are piezoelectric, generating electric voltage when compressed or expanding when voltage is applied, a property that comes from the lack of symmetry in the crystal structure. Atoms arranged in ways that create a net dipole moment, a separation of positive and negative charge, normally balanced but shifting when the crystal is deformed, pressure pushing atoms closer together or farther apart, changing the distances between positive and negative charges, creating a voltage across the crystal, small but measurable, useful in devices like microphones and speakers and sensors. Quartz watches using the piezoelectric effect to create oscillations, a thin slice of quartz vibrating at a precise frequency when voltage is applied, the vibrations countable, usable as a clock, more accurate than mechanical clocks because the frequency depends on the physical properties of the crystal, the dimensions and the elasticity, properties that don't change much with temperature or age, making quartz a reliable timekeeper. Billions of quartz watches depending on this property, on the connection between electrical and mechanical phenomena in crystals, a connection that exists because of how atoms are arranged asymmetrically without a center of inversion. Crystals can be grown artificially, synthesized in laboratories, conditions controlled to produce crystals that are larger or purer or more perfect than natural ones, sometimes for research and sometimes for industry. Silicon crystals grown for electronics, the base material for computer chips, grown as cylindrical ingots, single crystals with no boundaries, no defects, perfect order maintained throughout the entire ingot, atoms arranged in a diamond cubic structure, each silicon atom bonded to. For others, the pattern extending for inches or feet, billions and billions of atoms all in perfect alignment. The ingot then sliced into thin wafers, polished to atomic smoothness, used as substrates for building the complex layered structures that make up integrated circuits, processors and memory and all the components that make modern electronics possible. All of it depending on the properties of crystalline silicon, on the way electrons behave in a perfect crystal, able to move freely in some directions, blocked in others, the behavior tunable by adding impurities, doping the silicon with atoms that have more or fewer electrons than silicon, creating N-type or P-type material, building the junctions and gates and transistors that process information, that store data, that execute instructions, the foundation of computing resting on the properties of crystals, on materials that are ordered at the atomic level. Gemstones are sometimes grown artificially too, rubies and sapphires and emeralds, crystals that are chemically identical to natural ones but grown in hours or days rather than millions of years, the process accelerated by controlling conditions precisely, maintaining the right temperature and pressure and chemical environment, providing dissolved material that can crystallize, often growing the crystal from a seed, a small natural or synthetic crystal that serves as a template, providing a surface where new material can deposit, matching the existing structure, extending the pattern, the synthetic crystal growing with the same orientation as the seed, maintaining crystallographic alignment, producing a larger crystal that's continuous with the seed, the boundary between seed and new growth invisible or nearly so, both parts having the same structure, the same arrangement of atoms, indistinguishable except perhaps by isotopic analysis or by defects or inclusions that differ. Between natural and synthetic, tiny bubbles or particles trapped during growth, markers that reveal origin but don't affect the basic nature of the material, both natural and synthetic being crystals, both having ordered structures, both following the same physical principles. The size of crystals varies enormously, from single atoms in a regular arrangement at one extreme to massive formations weighing tons at the other, with most crystals falling somewhere in between, small enough to hold in a hand, large enough to see detail, to appreciate the faces and edges, the geometric forms that emerge from internal structure, each face representing a plane in the crystal lattice, a particular arrangement of atoms that creates a flat surface when the crystal breaks or when it grows, adding new layers parallel to that plane, building outward, the faces that grow slowest becoming the largest, the faces that grow fastest growing themselves out of existence or remaining small, the final shape of the crystal determined by the relative growth rates of different faces, which in turn depend on the atomic structure, on which planes have atoms closely spaced and which have atoms widely spaced, on how easy it is for new atoms to attach to each face, the complicated factors determining shape, making some crystals appear as cubes and others as octahedrons or prisms or complex combinations of forms, each shape characteristic of the material, recognizable to people who study crystals, who can identify minerals by their shape, by the angles between faces, angles that are constant for a given material regardless of crystal size, the angles determined by the internal lattice, by the geometry of the atomic arrangement. There's something satisfying about the connection between atomic structure and macroscopic form, the way something too small to see determines something visible, the way order at the nanometer scale creates order at the centimeter or meter scale, patterns repeating, fractals almost, though not quite fractals because the repetition has a limit, stops at the atomic level where individual atoms don't have internal crystal structure, are discrete objects with their own internal organization but not crystalline organization, the nucleus and electrons following quantum mechanical rules rather than crystallographic ones, though there are connections, quantum mechanics determining the size and shape of electron clouds, which determines how atoms bond, which determines how crystals form, everything connected, each level depending on the level below, built on it, emerging from it, the macro emerging from the micro through countless repetitions, through the cumulative effect of atoms following. Simple rules, rules that individually produce only local order, one atom bonding to its neighbors, but that collectively produce global order, the entire crystal organized, structured, patterned. Crystals can melt or dissolve, the ordered structure breaking down when temperature rises or when the crystal is placed in a solvent, atoms or molecules gaining enough energy to break free from their positions, to move independently, the crystal ceasing to exist as an organized solid and becoming a liquid or a solution, the atom still present but no longer fixed in place, no longer maintaining the pattern, the order lost, entropy increasing, which is what happens naturally unless energy is being added to maintain order, systems tending toward disorder, toward higher entropy, the second law of thermodynamics operating always, making it impossible to maintain perfect order indefinitely. Though crystals can persist for very long times, geological times, millions or billions of years, because the forces holding them together are strong, because breaking the bonds requires significant energy. Temperatures higher than ambient or conditions that aren't normally encountered. The crystal. Stable under most conditions, metastable under some conditions, unstable only under extreme conditions or in the presence of solvents that can disrupt the structure by surrounding individual atoms or molecules and pulling them away from the crystal, breaking bonds one at a time, the process of dissolution being the reverse of crystallization, taking apart what was built up, returning material to solution where it can move freely, can diffuse, can potentially crystallize again if conditions change. If the solution becomes supersaturated, the cycle of dissolution and crystallization part of the larger cycle of matter, materials changing form, moving between different states, solid and liquid and gas, depending on conditions, on temperature and pressure and chemical environment. Some crystals form in living organisms, biomineralization, the process of organisms creating minerals, shells and bones and teeth, all of them partially or entirely crystalline, calcium carbonate in shells, calcium phosphate in bones and teeth. The crystals grown in a controlled environment, inside cells or in extracellular spaces, organisms regulating conditions precisely, controlling where crystals form and what shape they take, using proteins to guide crystallization, to create structures that are more organized, more optimized for function than crystals that form inorganically, bones being composite materials, crystals embedded in protein matrix, the combination stronger than either component alone, harder than protein but tougher than pure crystal, able to flex slightly without breaking, able to resist fracture through mechanisms that pure crystals can't use, cracks deflecting around crystals, spreading energy over larger areas, preventing catastrophic failure. The structure. Engineered through evolution, refined over millions of years, tested by survival, optimized not perfectly but sufficiently, good enough to function, to support organisms, to enable life in forms that require hard parts, protective shells, internal skeletons, tools for biting and grinding, all made possible by the ability to create crystals, to build ordered structures from dissolved minerals, collecting them from the environment and concentrating them, arranging them, controlling their growth. There are crystals that form in pathological conditions too, kidney stones and gallstones, crystals precipitating where they shouldn't, accumulating into masses that cause pain, that block ducts, that require medical intervention, the body's normal regulatory mechanisms failing, allowing crystallization to occur in places where it's harmful, conditions becoming supersaturated with minerals that normally stay in solution, the crystals growing slowly, starting from tiny nuclei, dust particles or dead cells or aggregates of protein, any imperfection that can serve as a nucleation site, a surface where dissolved material can begin to deposit, building outward from that initial point, the stone growing over months or years, sometimes remaining small, sometimes growing large enough to cause problems, the crystals themselves not different from crystals that form elsewhere, same materials, same structures, just forming in the wrong place, context making them pathological rather than normal, the difference being location and effect rather than anything about the crystals themselves. Liquid crystals are something different, materials that have properties of both liquids and crystals, able to flow like liquids but having some degree of order, molecules aligned in particular directions even though they're not fixed in position, able to slide past each other but maintaining orientation, the alignment creating optical properties that are useful, especially the way liquid crystals respond to electric fields, changing their alignment, which changes how they interact with light. Whether they transmit it or block it, the property used in displays, LCD screens, liquid crystal displays, where electric fields are applied to tiny regions, pixels, changing the alignment in each pixel independently, controlling how much light passes through, creating images, the technology depending on the unusual properties of these materials that are neither quite liquid nor quite solid, existing in an intermediate state, ordered in some ways but not others, a phase of matter that doesn't fit neatly into the traditional categories, requiring new language, new concepts, liquid crystal being a term that sounds contradictory but that accurately describes the properties, the coexistence of flow and order, motion and alignment. Crystals in nature are rarely perfect, most of them containing defects, imperfections in the structure, atoms missing from where they should be or present where they shouldn't, vacancies and interstitials, or atoms of the wrong type substituted into the lattice, or entire planes of atoms displaced, dislocations, line defects where the crystal structure is disrupted along a line, the atoms on one side of the line slightly out of alignment with atoms on the other side, the mismatch creating strain, storing energy, making the crystal slightly less stable but not enough to cause it to break down. The defects often necessary for certain properties. For plasticity, the ability of metals to bend without breaking, deformation occurring through the motion of dislocations, planes of atoms sliding past each other along dislocation lines, allowing the metal to change shape while remaining solid, remaining crystalline, the structure adapting rather than fracturing, the presence of defects, making the material more useful, more practical, perfect crystals being brittle, breaking rather than bending, failing catastrophically rather than deforming gradually. The study of crystals, crystallography, has a long history, people noticing the regular shapes of crystals centuries ago, before microscopes, before any understanding of atoms, just the observation that crystals have faces that meet at consistent angles, that the same material always produces the same basic form even if the size varies, the insight that something about the internal structure determines the external shape, even without knowing what that internal structure was, without being able to see atoms or measure lattice spacing, just inference from macroscopic properties, from symmetry and angles, from the way crystals break, cleaving along certain planes more easily than others, preferring some directions over others, the preference indicating underlying order, underlying structure, anisotropy, direction-dependent properties that could only come from an ordered arrangement, from patterns rather than randomness. X-rays revealed crystal structure directly, diffraction patterns showing where atoms are located, the method working because X-rays have wavelengths similar to the spacing between atoms, allowing them to interact with the crystal lattice, to scatter off individual atoms, the scattered rays interfering with each other, reinforcing in some directions and canceling in others, creating patterns of spots, diffraction patterns that can be analyzed to determine the positions of atoms, to reconstruct the three-dimensional structure of the crystal, the technique powerful in general, applicable to any crystalline material, used to determine the structures of minerals and metals and proteins, revealing the atomic arrangements that underlie properties, showing exactly how atoms are positioned, what bonds connect them, what angles and distances characterize the structure, information that's fundamental to understanding materials, to predicting properties, to designing new materials with desired characteristics. Proteins can crystallize, large biological molecules arranging themselves into ordered arrays. Though the process is tricky, requiring precise conditions, the right concentration and pH and temperature and often additives. Molecules that help stabilize the protein or exclude water or otherwise promote crystallization. The resulting crystals usually small, sometimes microscopic, but large enough to study with X-rays, the diffraction patterns revealing the protein's structure, the exact shape of the molecule, how the chain of amino acids folds into a specific three-dimensional form, the structure determining function, active sites and binding pockets shaped to interact with specific other molecules, the fit precise, the shapes complementary, the whole system depending on structure, on the exact positions of atoms, differences of fractions of a nanometer changing whether a molecule binds or doesn't bind, whether a reaction occurs or doesn't occur, the precision extreme, the margins. Tight, yet the system works, proteins folding reliably into their functional forms, maintaining those forms long enough to do their jobs, the structure stable but not permanent, proteins eventually degrading, being broken down and recycled, their components reused, the cycle of synthesis and degradation continuous, the cell maintaining populations of proteins, producing them as needed, destroying them when they're no longer needed or when they're damaged. Ice crystals form in different structures depending on conditions, ordinary ice being ice IH, hexagonal, but there are many other forms, ice 2 through ice 15 and beyond, different arrangements of water molecules that are stable under different combinations of temperature and pressure, most of them stable only at high pressure, not naturally occurring on Earth's surface but possibly present inside icy moons orbiting Jupiter or Saturn, where the weight of overlying ice creates pressures that stabilize high-pressure phases, creating layers, ice IH at the surface transitioning to other forms at depth, the exact boundaries depending on temperature and pressure profiles, on how heat flows through the ice and how pressure increases with depth, the interior structure of these moons probably complex, layered, possibly containing liquid water beneath the ice if tidal heating provides enough energy to melt ice at depth, creating subglacial oceans, environments that are protected from the vacuum of space, insulated by miles of ice, possibly warm enough for liquid water to exist, possibly containing dissolved minerals, possibly even harboring life, though that's speculation, hopeful thinking based on the presence of water and energy, ingredients that seem necessary for life but that aren't sufficient, that don't guarantee life, just make it possible, maybe. Crystals are common throughout the universe, probably anywhere matter accumulates and conditions allow atoms to settle into stable arrangements, which presumably happens frequently, planets and moons and asteroids all containing minerals, all having crystalline materials in their interiors or on their surfaces, though the specific minerals would vary depending on composition and history, what elements were available when the body formed, what processes occurred afterward, heating and cooling, and chemical reactions, impacts and differentiation, the heavy elements sinking toward the center and light elements rising toward the surface, creating layered structures, cores and mantles and crusts, each layer having different composition and thus different minerals, different crystals, the exact details unknown for most bodies, known only for places that have been visited by spacecraft or where samples have been collected and analyzed, meteorites providing some information, pieces of asteroids that fell to Earth, bits of the early solar system preserved in rock, some of them containing crystals that are older than Earth, pre-solar grains, minerals that formed around other stars and survived the formation of the solar system, now embedded in meteorites, tiny messengers from the distant past and distant places, carrying information about conditions elsewhere, about other stars, other environments, written in isotopic ratios and crystal structures, readable by those who know how to interpret them. There's a certain timelessness to crystals, the structure unchanging once formed, atoms locked in place, persisting for as long as conditions remain stable, which in some cases is billions of years, crystals being among the oldest objects accessible, zircon crystals preserving information about Earth's early history, some of them dated to over 4 billion years old, almost as old as the planet itself, surviving through everything that's happened since, through impacts and volcanism and mountain building and erosion, small enough to be transported but durable enough not to be destroyed, carried by water and deposited in sediments, incorporated into rocks that form and are eroded again. The crystals passing through multiple cycles, recycled but not destroyed, maintaining their internal structure, maintaining the information they contain, ratios of isotopes that reveal when they formed, what temperature they formed at, perhaps even whether water was present, clues written in the crystal lattice, accessible through careful analysis, through techniques that measure compositions at microscopic scales, pulling information from tiny volumes, reconstructing history from fragments. Quartz sand on beaches, each grain a crystal or a piece of one, worn smooth by tumbling, by grinding against other grains, the edges knocked off, the faces rounded, but the internal structure intact, atoms still arranged in their characteristic pattern. The material still recognizably quartz even though the shape has changed. The properties the same, hardness and density and optical characteristics unaffected by the loss of crystalline faces. The crystal defined more by its internal structure than by its external form, the shape being consequence rather than cause, determined by the structure but not essential to it, a crystal ground to a sphere still being a crystal, still having ordered atomic arrangement, the definition based on internal order rather than external appearance. Though historically the reverse was true, crystals being defined by their shapes before anyone understood what caused those shapes, the geometric forms being the defining characteristic, the feature that made something a crystal, understanding evolving over time as tools improved, as techniques developed for seeing smaller and smaller scales, eventually reaching the atomic level and revealing that crystals are ordered arrangements of atoms, definitions shifting from macroscopic to microscopic, from observed properties to underlying causes. Some materials are difficult to crystallize, glass being the classic example, silicon dioxide like quartz but cooled too quickly to crystallize, atoms frozen in disordered positions, the material solid but not crystalline, lacking the long-range order that defines crystals, having only short-range order, each silicon bonded to 4 oxygens and each oxygen bonded to 2 silicons but the network not regular, not repeating, angles and distances varying, the structure random on large scales even. Though it's constrained on small scales by bonding requirements, glass being an amorphous solid, a frozen liquid, sometimes called a supercooled liquid, though that's controversial, debated, the properties not quite matching either category, glass being another intermediate case, another material that doesn't fit neatly into traditional classifications, requiring its own category, its own terminology, amorphous solids being common actually polymers and rubbers and many biological materials. Being disordered, lacking crystal structure, functioning without needing the order that crystals have, sometimes even requiring disorder, flexibility, and toughness coming from the ability of disordered chains to slide and rearrange, to absorb energy through motion rather than through breaking bonds, the lack of order being an advantage in some contexts, a feature rather than a flaw. Crystals can be shaped and polished, cut along specific orientations to expose particular faces, angles calculated to maximize beauty or optical performance, gemstones being cut to enhance brilliance, to direct light into and out of the stone in ways that create sparkle, fire, dispersion of white light into colors, rainbows flashing inside the stone, the effect depending on the angles of the cuts, on the refractive index of the material, on how much light bends when entering the stone, how much reflects at internal faces, total internal reflection trapping light inside, bouncing it around until it exits through the top, the table, visible to the viewer, the cutting being a skill, an art informed by science, by understanding of optics and crystal structure, knowing which directions to cut, what angles to use, how many facets to include, balancing complexity against brilliance, maximizing the effect while maintaining structural integrity, not making the stone so thin or delicate that it's vulnerable to damage, practical considerations constraining aesthetic choices, though sometimes aesthetic wins, spectacularly cut stones that are fragile, beautiful but impractical, display pieces rather than jewelry, meant to be looked at rather than worn. In cold places, ice crystals coat surfaces, frost forming overnight when temperature drops and moisture condenses directly from vapor to solid, creating feathery patterns on windows, delicate structures that look like ferns or trees, dendritic growth, branching patterns that emerge from the way crystals grow, some directions growing faster than others, tips extending, creating branches, side branches forming on the main branches. Fractal-like patterns, though not true fractals, the repetition. Limited, not infinite, but striking nonetheless, beautiful in their complexity, their intricacy, patterns that are ordered but not regular, predictable in general form but unique in detail. No two frost patterns exactly alike because the exact sequence of growth depends on local conditions. Tiny variations in temperature or humidity affecting which branches grow and how far, creating diversity within the constraints of hexagonal symmetry. The underlying crystal structure expressing itself in the macroscale pattern but not determining it completely, leaving room for chance, for randomness, for individuality. Crystals growing in the lab are often simpler, purer, grown under controlled conditions that eliminate many of the factors that create complexity in natural crystals, the result being regular shapes, clean faces, uniform color, crystals that look almost artificial even though they're still natural in the sense of being formed through natural processes, just processes that are controlled, guided, optimized for particular outcomes, growing large single crystals or specific shapes or materials. With particular purity levels, the control allowing production of crystals that are better for certain purposes than natural crystals, more reliable, more consistent, easier to work with, though lacking perhaps the character of natural crystals, the irregularities and inclusions and color variations that make each natural crystal unique, interesting, worth collecting for its own sake rather than for any use, valued for being itself rather than for being perfect. The largest natural crystals are found in pegmatites, igneous rocks that form from the last portion of magma to crystallize, enriched in water and in elements that don't fit well into common minerals, the water lowering the melting point and allowing crystals to grow larger. Atoms having more mobility in the water-rich melt, able to move farther to reach growing crystal faces, building larger structures, crystals in pegmatites sometimes measuring feet or yards, enormous compared to typical crystals, sheets of mica large enough to be used as windows, crystals of feldspar or quartz weighing tons, growing because conditions allowed it, because cooling was slow and material was available and nothing disrupted the process, time and stability combining to produce size. The opposite of what happens in volcanic rocks where cooling is rapid and crystals are small or absent, the same material producing very different results depending on how it forms. Slow cooling giving large crystals, rapid cooling giving small crystals or glass, intermediate rates giving intermediate sizes, the relationship direct and predictable, used by geologists to interpret history, to determine how rocks formed by looking at crystal size, inferring cooling rate, reconstructing conditions that existed when the rock was forming, reading stories written in stone, in crystal structure and texture. There are crystals floating in the atmosphere, ice crystals high in the troposphere, cirrus clouds made of tiny ice crystals, each one a complex geometric form, growing in cold air at high altitude where temperature is well below freezing, water vapor crystallizing directly, no liquid phase, building snowflakes that drift slowly downward or are carried upward by updrafts, persisting for hours or days, sometimes long enough to grow large, to develop elaborate structures before eventually descending into warmer air and melting, disappearing, returning to vapor or falling as rain if they descend far enough, the cycle continuing, water moving between different states, solid and liquid and gas, up and down through the atmosphere, crystals forming and melting over and over, the same molecules participating countless times, the same water that's been on Earth for billions of years, cycling through organisms and oceans and ice caps and atmosphere, some of it locked in crystals for periods, trapped in glaciers for thousands of years before melting and returning to circulation, some of it spending time in deep aquifers, groundwater moving slowly through rock, taking decades or centuries to travel from where it infiltrates to where it emerges at springs or wells, and during that time perhaps interacting with minerals, dissolving small amounts, carrying them in solution, the water eventually evaporating and depositing those minerals somewhere else, transporting material gradually, particle by particle, contributing to erosion and deposition, to the slow reshaping of the landscape, imperceptible on human timescales but significant over geological time, over millions of years when mountains can be worn to plains and new mountains can rise, the surface of the planet in constant slow flux, driven partly by water, by its ability to dissolve and transport and deposit, to break down rock and carry away the pieces, to precipitate minerals in new locations, to form crystals in caves and cracks and veins, to build up deposits that eventually become new rock, the cycle of rock formation and destruction mediated by crystals, by crystallization and dissolution, processes that are fundamental to geology, to the way the solid earth changes over time. Crystals are everywhere, really, most solid materials being at least partially crystalline, metals and ceramics and many minerals, the exceptions being glasses and polymers and amorphous materials, but even those sometimes contain small crystalline regions, microscopic crystals embedded in otherwise disordered material, the crystalline and amorphous coexisting, boundaries between them sharp at the atomic level but gradual macroscopically, regions of order separated by regions of disorder, the mixture having properties that depend on both, sometimes combining advantages of each, crystalline regions providing strength and amorphous regions providing toughness, the composite being better than either pure form, though pure also isn't quite right because perfect purity is impossible, every material containing some impurities, some defects, the question being how much, how many, whether they're significant or negligible, whether they affect properties in measurable ways or whether they can be ignored, the answer depending on what properties matter. For some applications, trace impurities are critical, affecting electronic properties or optical properties or catalytic activity, parts per million or parts per billion making the difference between useful and useless, requiring careful control, careful purification, sometimes requiring synthesis rather than extraction from natural sources, growing crystals from pure starting materials, building up structures atom by atom or molecule by molecule, controlling composition precisely, achieving purity that nature never produces though at cost, at expense of time and energy and resources, the effort justified when purity matters, when the application demands it, when nothing else will work. The geometry of crystals reflects the underlying symmetry of the atomic lattice. All crystals belonging to one of 7 crystal systems based on the angles and lengths of their unit cell edges, cubic or tetragonal or orthorhombic or hexagonal or trigonal or monoclinic or triclinic, each system having characteristic symmetry elements, rotation axes and mirror planes and inversion centers, the combination of these elements defining the point group, the set of symmetry operations that leave the crystal looking unchanged, mathematical descriptions of how the crystal can be rotated or reflected, abstract properties that have physical manifestations, determining what faces appear, what angles they make, what overall shape emerges, the classification system being hierarchical, systems subdivided into crystal classes, further subdivided into space groups that describe not just the point symmetry but also how the pattern repeats in 3 dimensions, how the unit cell tiles to fill space, 230 possible space groups covering all possible combinations of symmetry elements and translations, every crystal belonging to one of these groups, all of them discovered and catalogued in the 19th century through purely mathematical analysis, working out what combinations are possible, what patterns can repeat in 3 dimensions without gaps or overlaps, the analysis complete before anyone could see atoms, before there was any way to verify which space group a particular material belong to the theory preceding experimental verification by decades, one of those cases where mathematics predicted reality, where abstract reasoning revealed truths about the physical world. There's a quietness to thinking about crystals, about atoms arranged in repeating patterns, the order that exists at scales too small to see but that manifests in forms that are visible, beautiful, patterned, predictable, the connection between micro and macro direct and mathematical and somehow peaceful, satisfying, knowing that the shape follows from structure, that nothing is arbitrary, that angles appear because atoms are spaced in certain ways, that faces emerge because planes of atoms terminate at the surface, that everything is determined by simple rules applied consistently, over and over, no intelligence required, no planning, just physics and chemistry doing what they must do, creating order because ordered arrangements are stable, because energy is minimized, because nature finds equilibrium, settles into configurations that are lowest energy or at least locally lowest energy. Metastable states that persist because there's no easy path to lower energy, the system. Trapped in a minimum, good enough, stable enough, existing perhaps not forever but for very long times, geological times, spans that make human concerns seem brief, temporary, small. Somewhere deep in the earth right now, in darkness and heat and pressure that would be unimaginable at the surface, atoms are finding each other, arranging themselves, a crystal growing that no one will ever see, that might never reach the surface, that might remain buried for the entire remaining lifetime of the planet, growing slowly in conditions that are stable, that change so gradually that the change is imperceptible, temperature rising by a degree over 1,000,000 years perhaps, pressure increasing as more rock accumulates above. But the change is slow enough that the crystal persists, adapts, continues growing or stops growing or begins dissolving, whatever the conditions require, the crystal having no preference, no desire, no awareness, just existing as matter must exist under those conditions, following the rules that govern how atoms interact, how they bond and arrange themselves, the crystal a record of conditions, of temperature and pressure and chemical environment, information encoded in its structure, in the spacing of atoms and the types of impurities incorporated and the pattern of growth zones, layers that might be visible under magnification, each layer representing a period of growth, conditions at that time, changes marked by changes in color or clarity or crystal orientation, subtle variations that would tell a story to anyone who could read them, who knew how to interpret the signs, though the crystal sits unread, growing in silence and darkness, patient and persistent, existing without purpose, without meaning, just being what it is, atoms in an ordered arrangement, a pattern that repeats, stable for now, perhaps stable for billions of years, a small ordered region in a vast disordered universe, a temporary victory over entropy, maintained not through effort but through the simple fact that this arrangement is stable here, now, under these conditions, and will remain so until something changes, until temperature or pressure or chemistry shifts enough to make the current arrangement unstable, and then the crystal will transform or dissolve, returning its atoms to the random motion of liquid or gas, the order breaking down, disappearing, the pattern lost, though the atoms remain, ready to form new patterns, new crystals, when conditions allow, the cycle continuing, matter moving between order and disorder, crystallizing and melting, forming and dissolving, endlessly, patiently, without urgency, following physical laws that operate the same everywhere, always in darkness kilometers below the surface and in the cold thin air of the upper atmosphere and in the moderate conditions at the surface where humans live, where crystals can be found and collected and studied and admired, where their beauty is visible, their patterns obvious, their existence a reminder that order emerges naturally, that complexity arises from simplicity, that patterns form when conditions allow, that the universe creates structure. Spontaneously, without needing intention or guidance, just time and matter and the laws of physics, operating together, producing crystals,